In the previous lecture, we computed the associated matrix of the axial symmetry about an axis in R2, fixing a pair of bases in the domain and in the codomain, purposely chosen following the problem we were facing. At the end, we noticed that in order to find the image of a vector that was different from the basis vector in the domain, we had to follow a procedure that involved finding a solution of a system of linear equations. This implies that having the associated matrix with respect of a generic basis of the domain and the codomain, usually it will not be easy from that to recover all the information contained in the homomorphism. It will not be easy to compute the images of many other elements in the domain, since at each step we have to solve a system of linear equations. We ask ourselves if there is a way of maybe choosing a different kind of basis in the domain and in the codomain that would help us to recover the homomorphism we are starting from the associated matrix, without having to solve at each step systems of linear equations. The answer is yes. There is a basis if the vector space domain and codomain are Euclidean, so they are kind of Rn. But finding the associated matrix to an homomorphism with respect of this basis at first might be very complicated. We will derive a formula which is extremely helpful in finding the coordinate form of an homomorphism. Motivation. We mentioned several times about the importance of having an homomorphism expressed in coordinates, should we wish to exploit the map itself. If f is linear from Rn to Rk, having f expressed in coordinates is the same as computing the associated matrix with respect of the canonical basis of the domain and the codomain. This is a fundamental remark, exactly what I've just said. If we are able to express f with respect of the canonical basis, then we will not need to solve systems of linear equations to recover f. More precisely, we will still need to solve systems of linear equations, but being the canonical basis, being the basis we are considering canonical, we don't really need to make any computation to solve these systems of linear equations. Therefore, we are in the situation in which, in order to find f, we allowed ourselves to choose clever bases of the domain and the codomain. But then we want really to express the associated matrix in function of the canonical basis. So how do we pass from an associated matrix with respect of some clever basis of domain and codomain to the associated matrix with respect of canonical basis of domain and codomain? Well, this is the argument we will cover in this lecture. Let A be the associated matrix of F with respect of the canonical basis. Let's see why the statement in yellow is true. Let's compute the image through F of a generic vector x1, xn in the domain by using the procedure explained in lectures 9.4 and 9.5, even numerically in 9.5. Notice that writing f of x1 through xn as a k-tuple over k is expressing f in coordinates. So let's go through the same procedure. First step, express x1, xn as a linear combination of the bases that we have chosen of the domain, in this case the canonical basis. So we want to find the coefficients of this expression. Remember that the coefficients were denoted by lambda i's in the lectures 9.4 and 9.5. And so we want to find lambda i's such that this vector here on the left hand side equals lambda 1 times e1 plus lambda 2 times e2 and so on. But it is immediate, so these require finding the solution of a system of linear equations with n equations and n unknowns. But since E1, E2, En are the canonical bases, we immediately see that the lambda i's must be the xi's for every I. So this step is basically skipped. We don't need to make any computation to solve this system if the vectors are the canonical bases. Step number 2 was to compute the column vector given by the product of the coefficients of this linear combination of step 1, which we computed to be x1 through xn, multiplied on the left by the associated matrix. And the result we denoted as mu i's, and these mu i's are the coefficients of the linear combination that we will use to compute the image of the vector we started from. Indeed, in the steps 3, we have that the image f of x1, xn is going to be the linear combination with the mu I times the basis of the codomain, which in this case is still the canonical basis. Okay, remember that we are looking at the associated matrix with respect of ej and ei. So this amounts simply to take the row vector given by the coefficients mu I, because each ei is the canonical basis, and expanding this linear combination, we precisely get this vector mu I written as a row vector instead of column vector. And in particular, from the equality in the step 2, we see that this is just a transpose of this vector. The conclusion is that in the expression in coordinates, fi's are precisely the coefficients of the column vector a multiplied on the right by the column vector x1 through xn. So basically I take the vector of which I want to get the image, I multiply on the left by the associated matrix with respect of the canonical basis, and what I get is precisely, as a column vector, the image of x1 through xn without needing to solve any system of linear equations. And if we start from a generic vector, this will be precisely the coefficients. The first coefficient of this product is going to be precisely f1 of x1 through xn. The second coefficient of this product is going to be f2 of x1 through xn, and so on. So this proves the claim that having the associated matrix with respect of the canonical basis is the same as having f in coordinates. We just need to perform this multiplication of the generic vector x1 through xn on the left by the matrix A. As mentioned before in lectures 9.3 and 9.5, we have seen that to determine a homomorphism, it is helpful to use the flexibility of being able to choose clever bases. So I would add both to determine an homomorphism and even to express it in terms of its associated matrix. The resulting expression of the homomorphism will require lengthy computation for exploiting. In particular case, we have seen that we have to solve systems of linear equations to explicitly recover the homomorphism from the associated matrix. Hence the need of some formula for passing from the associated matrix with respect of a clever choice of basis of the domain and the codomain to the associated matrix with respect of the canonical basis of domain and codomain. And this is exactly what we are going to state right now. Theorem, which we will call basis change theorem. Let f be an homomorphism. Now we fix two bases of the domain and two bases of the codomain. The first basis we will use the same notation as before. Therefore, they will be called Vj and Wi. The second basis, they will get a prime indication as a subscript. Hence, they will be denoted as Vj prime and Wi prime, according with the fact that they are in the domain or the codomain. Now, we assume furthermore that the dimension of V and W, which are respectively n and k, will be finite. Then we conclude the following equality, which is absolutely fundamental. We see that the associated matrix of F with respect of the prime basis is related to the associated matrix computed with the usual matrices Vj and Wi, and the relation involves multiplications by two new matrices, one on the right and another one on the left. The matrix that multiplies on the right, we call P, has coefficients P, H, J, and the one whose inverse multiplies on the left is called Q, and its coefficients are QSI. P is defined in the following way. The coefficients occur in the linear combinations that express the vectors of the basis, the prime basis. Let's call it the vectors of the new basis. New basis is the one with the prime, in function of the vectors of the old basis of the domain. If we fix J and we express Vj prime as a linear combination of the old basis, we see that Phj, in Phj it is the first index that varies, because the first index follows the index of the old basis. So when we compute in practice these linear combinations expressing the new basis in function of the old, when we find the coefficients, we have to write them as column vectors in order to determine P. Because when H varies, P has the first coefficient that varies. And being P, the matrix whose coefficient is Phj, I'm running through the jth column. Here, this coefficient span the jth column in P. And the same holds for the matrix Q. So both P and Q are constructed column-wise, solving these systems of linear equations, expressing Vj prime in function of the old basis and expresses Wi prime in function of the old basis of the codomain. P and Q, I repeat, they are constructed column-wise. The matrices P and Q are called the changement of basis matrices, as they express the new bases in function of the old ones. Notice that they are built column-wise, just like the matrix AF, the associated matrix to the homomorphism F. In the next lecture, we will see few applications.